All right, everybody. Yeah, so we'll move on to another exciting frontier, another exciting step in your journey to become applied stats practitioners using R. We're going to, basically in lesson 1, we just barely got introduced to mixed models. In lesson 2, we're going to do another few mixed models and get a little bit more into it. So now we're really getting a little more into the stat modeling side of things. And so as usual, we have the full text version that you can look at, which has all the code in it. And we have the slides. So I'll go ahead and get started with that. Yep, so same stuff. So yeah, we're gonna keep talking about trying to go from data to some final product, the data to doc pipeline. And we're gonna talk about how to fit a linear mixed model to a couple different common type of experimental design that you would see in ag science. So hopefully this could be relevant to some of you all. And we're going to learn what estimated marginal means or least square means are. That's like a way we can use our model to make predictions. And once again, we're going to go through that same pipeline as usual, starting with an external file, do the, explore the data, fit a model, and compare different ones. We're going to get a little bit more into the idea of random intercepts and random slopes as well, which I just touched on before. And we have the same. So yeah, if you go to your Posit Cloud workspace, so yeah, you can go ahead and close the worksheet from the previous one. Oh, by the way, so if you made notes in the worksheet or anything and you're on Posit Cloud, you can actually export that file and download it to your local computer if you want to. If you just, let's say, see, I just saved the change to this worksheet. If I check on it and then go to more, export, that's how you could download it. Because I can't guarantee how long you will have access. I'll keep this workspace online for as long as possible, but eventually I may have to delete it to make room for newer lessons. And so this is only, you might want to, if you saved any text you want to keep in there, you should either copy and paste it locally or download it, whichever you want to do. So I'll close everything. Now I would, if you exit this, it will save the image of that, and you can come back to this anytime you want. Yeah, so everything will. Oh, and the file, I think you do have to save it as you go along. Yes. And yeah, what I would recommend doing now, just to make sure that we're all starting with the same state, everything clean, I'm going to go ahead and restart R. So I'm going to go to session, and I'm going to restart R. That will get rid of all the packages that are loaded right now. They'll still be installed, they just won't be loaded. And I'm also going to delete everything in the workspace. I'm going to do that by pressing this broom button. And that'll just clear everything from lesson 1 away. So now we're just starting on, just to make sure that everyone's code runs the same, we'll make sure that everything is deleted so that there's not other objects in the background that might influence what the results you get. And you can also clear your output if you press this broom here too. Now everything looks nice and clean. And we'll open up worksheet number 2, lesson 2 worksheet in the worksheets folder. Any questions? Okay, so the same drill as last time. We're going to start by loading the packages. We're going to use LME4 again, and that is a mixed model package, but it's kind of limited in the types of models it can fit and the types of model structures it can deal with. For more complicated, we're not going to get into them today, but for more complicated models, there's other alternatives, other R packages that you should look into. But for the simple experimental design we're going to be looking at and simple error structure, the LME4 will do just fine. So first we'll load all the packages. So just go ahead and load the packages. And by the way, I also put this line theme set in there, which will make all the plots that we do show up in a nice color scheme. That's just nice for visualization. So we'll do that. So we'll run all that. Now, the data set that we are going to work with today, I'm not really sure exactly where it comes from, but I found it on an R blog post, and it's supposedly from a agronomic experiment looking at the yield of different genotypes of different lines of fava bean under different treatments. So it's a classic genotype by treatment agronomic experiment, like many of you probably know about. And that's what you can use to make some delicious food with and everything like that. So you can compare the yield of 6 different genotypes under 2 different treatments. So it's a 6x2 factorial experiment. You have 6 genotypes and 2 treatments. They sow the seeds in the spring and the autumn and try to see if either of those treatments affects yield, and whether, if so, does it do differently by genotype. And the experimental design is a split plot. I'll show if people, some of you may know what this is, others may not. So I'm going to go through exactly what that means. It's a classic type of design in ag science. Basically, it means that you have one, if you have more than one thing you're manipulating, like we're manipulating the sowing time and we're also manipulating the genotype, we have 2 factors. We usually, in a field, there's sort of larger areas that are called main plots, and then those are divided up into subplots. And so basically what it means is that every subplot in a main plot gets the same sowing time treatment, but it's split up by genotype. And so there's 12 combinations, right? Two treatments and 6 genotypes. There's 12 possible combinations. So a block in this experiment means all 12 possibilities, each with its own plot. And so we've got an entire block would have 12 subplots in it. And that whole thing is replicated 4 times. And then they took that whole thing, those 48, and replicated that in 2 different locations. And then not only did they do that, they also repeated that entire thing, 2 locations, each with 48 plots, 3 seasons in a row. So let's go through that in pictures so you can understand. This is a main plot. Half of it, they sowed the seeds in the autumn, half in the spring. That's what one main plot looks like. Then they split up those main plots into subplots for each genotype. And notice, by the way, that the order of it is randomized each time, right? You do the genotypes in a different order every time because it's important to randomize when you set up an experiment. Like what if there's, G1 has a different yield when it's right next to G2 or something? I mean, that's not likely, but you never know. So it's better to randomize and make sure to get rid of that possibility. Right. And so that whole thing is a block. Some people call it a rep. And they replicated that 4 times. And notice that every time you replicate, you not only randomize the genotypes, you also randomize the treatment positioning as well. It's different. You want to randomize it every time. That's just good experimental design for you. So that's like one whole location, got 4 blocks. Then they're like, okay, we did it at 2 locations, Badiola and Papiano, and we did it at 3 different years as well. And so this is like what all the data from the experiment would be. And so we, just for simplicity in this case, we're considering the combination of location and year to be an environment. And that's commonly done in agronomic studies just for simplicity. So we're saying there's 6 environments. If we're looking at genotype by environment interaction, we're calling one time point at one place an environment. We're not going to worry about the fact that, like, okay, Badiola in 2001 is probably more similar to itself at a different year than it is to the other place. We're not going to care about that. But another point of experimental design is, well, we want to have a lot of replication within each environment so we can make sure we estimate that environment's effect very well. And we also want to repeat the experiment as many environments as possible so we can look at the generality of our treatment effects and our genotype effects and see patterns if they hold across many environments. It's good to replicate a lot within each environment, but especially important to do your study as many environments as possible. Because if you see an effect, you don't want to just say, is it true in my one little plot? You want to say, is it true everywhere? And so the more environments you do, the better. Okay, so we're going to pull in the data from a file, which I put on the cloud server, called it fava.csv. You can also I put it on the GitHub site as well. So if you're doing this on your own machine, you can run it there. And so we're going to use the read_CSV function again, as we did in the this morning. Control Enter Fava. You can see it comes out with 288 rows and 6 columns. And if you're doing this on your own machine, just delete this comment and run that line, and it will pull the CSV in from the website. We can look at the data in a couple different ways. We could just type the name of it into the console and hit enter, and that will automatically give you the first few rows and some summary information. So we could just do that. So let's, yeah, we'll just go into the console here and type Fava and hit enter. And it'll give us you can see we have 6 columns. The location, you can see its character because there's 2 text identifiers. The year, this is also character because it has like a hyphen in it, 2002-2003. So R is reading that in as just a text string. The 2 sewing treatments, their genotypes have different names. It says what block that measurement comes from and the yield. That's the only sort of response variable. The only quantitative data we have here is just yield. That's all we care about in this case. And oh yeah, and you can use glimpse as well to get a sort of more concise way to see that. I just want to show you that. There's glimpse. Same idea. Okay, and I told you a minute ago that we were going to treat the combination of location and year as an environment in our statistical model. Well, in order to do that, you actually need to create a new column in the data, which is basically pasting the location and year text together to make a new column. That's how you do it in SAS with the data step. Does anyone want to guess what function we would use in R to do this, which we learned this morning? I heard someone say mutate. It probably says it on the thing. But anyway, mutate, right? We're creating a new column out of some other columns that already exist. So that's what we're going to do. And we have to do a few different things. We're going to, I didn't talk about factor variables yet. We've so far only seen numeric and character. There's another type of data called factor. Factor is a data type that can only have a preset. The data can only take one of a few preset values. So like in an experimental design, a factor, the sewing treatment can only have 2 different values, spring or autumn. So it makes sense to model it as a factor data type in R. That way, we're sure that any of those, that column will only contain those 2 different values, spring and autumn. And that's especially important to do with this block column because the block is 1, 2, 3, 4. It's actually being coded as a numerical variable right now, which doesn't make sense because it's not like block 4 is 4 times bigger than block 1. Those are just IDs. So it makes sense to convert that to a factor variable so that we make sure we don't accidentally treat it as a number that can be added and multiplied and that kind of thing. It's just an it could be called A, B, C, D. It's just called 1, 2, 3, 4. We're going to make sure that it is. This actually happened in a paper that was in like Science or PNAS or something. They had a some analysis that was done at a global, I don't know if it was R, but it was some software they used. The analysis was done globally. They had country as a predictor, but somehow the country was a numeric identifier. So like, whatever, Albania was 1, Algeria was 2, and going on. And then they put that in their statistical model and found like country had a huge impact on something. But it's like, well, you just said that Algeria was 2 times Albania or whatever. So that had to be retracted. So that's like a good reason to always set your numerical IDs as factors if that's what you're doing. Yeah, so first off, we're going to mutate across means for you can apply the same function to a lot of different columns. So it says across location through block, turn all those columns to factors. Location : block means all columns from location to block. We turn them into a factor. If you look, you've got location, year, sowing, genotype, and block. All 5 of those columns we can turn into factors. They're all discrete ones with only a few possible values. So we're going to change into factors. And then, so we're going to use mutate for that. And we're going to say across from location to block, we're going to apply the function factor. So turn them all to factors. And then we're going to use the interaction function, which means create a new variable called environment, which is the interaction of location and year. Just paste location and year together and make a new factor out of it. So if we hit Control Enter on this code block, we can see Fava now has 7 variables. If we look at Fava again, yeah, we can see environment is a new call. It also has FCT for factor, including environment. So this is Papiano 2002 through 2003 is its own new column. So it has 6 possible values in it. There's 2 environments in 3 years, or 2 locations in 3 years. So there's 6 environments. Okay, and we're going to make some exploratory plots. I just gave the SAS code in case anyone is a glutton for punishment and wants to look at the SAS code, but we are going to look at the distribution of yield under these different combinations. We're going to use geom box plot. We're going to use box plots to look at the distribution of yield. Box plot shows you the median, the central 50% of the data, and where essentially everything except outliers is found. And first, so I showed you different ways to do it. First, we can just do it by genotype, just by genotype. So we want, for each genotype, a box plot of yield. So genotype on the x-axis, yield on the y-axis. And we're going to say Fava is the data frame where we want to plot from. And so let's do that first off. So first, and by the way, R is case sensitive. If you notice, the columns in this data all start with capital letter. So we have to type in genotype capitalized, and yield is capitalized here too. And then geom underscore box plot means what type of plot are we going to draw? We're going to draw a box plot. So there's our plots. You can see if we just like ignore location and we ignore treatment and everything, all of them kind of have the similar distribution for yield. It's like a median of 3 or 4. And there's the sort of the middle 50% of the data are found in this box. Okay, that's just one for yield. Well, what if we also want to plot? Obviously, this experiment is looking at the interaction between genotype and sowing treatment. So let's make a box plot of each combination of genotype and sowing treatment. So we say, okay, we still want genotype on the x-axis and yield on the y-axis, but now we want fill equals sowing. That means fill in the box plots by color of what treatment, sowing treatment they come from. And group equals interaction, genotype, and sowing. We want to, for each genotype, split up and make a separate box plot for each combination of genotype and sowing. So we want, that's what we're doing here. So fill equals sowing and group equals interaction of genotype and sowing. So we would say fill and group. now you can see, okay, we're starting to see there's clearly some effect of sowing, right? The autumn has a higher median yield and it doesn't really look like there's that much of an interaction, right? Like if there were to be an interaction, some genotypes might have higher in spring than autumn, and some would have higher in autumn than spring. But if there is an interaction, it's not very strong because pretty much every time the autumn is doing better than spring. So there's not a strong interaction between treatment and genotype. That's what I would say from looking at this. Although the treatment has an effect, it doesn't have an interaction with the genotype very much. But we also said, well, this experiment was done at different locations and years, so why don't we, this is just lumping everything together. Let's also make a plot even more finely divided and split up this whole thing, make 6 of these, one for each combination of location and year. How are we going to do that? We have to add another line to this plotting code. Facet underscore grid means make a grid of panels based on some variables in the data. And we're going to do the combination of location and year, location by year. So locations going down and years going across. It's going to make 6 box plot. Yeah, a lot. 6 panels each have 12 box plots on them. But I mean, that's how they did this experiment. So that's what we're going to take a look at. Okay, so what can we say about this? Does anybody want to comment on these box plots? What can you say from looking at them? Is there an interaction between environment and genotype? Well, first of all, do these 6 environments have different yields? Yes or no? I would say yes, right? Like especially these 2002 years, both of the yields are quite low, right? So it's like maybe that was just a bad year for beans in Italy or whatever. And is there an interaction between genotype and environment? I would say kind of, right? At least because in 2001, 2002, you can see there's like this genotype had a high yield and this one had lower, but in another year they had no difference. So it's like, well, there's an interaction, a G by E interaction, right? In some environments, the genotypes have a different yield. In others, they have all the same. That's a G by E interaction. So we can say, yes, there's something going on here. If we did a stat model that ignored environment, it would be bad because it would say there's no difference, but actually there is an interaction with G by E. So we better take that into account. And so yes, this that the key message you should take from that is, first of all, it's important to have data from different environments. If you have an experiment, it's good to repeat it under different conditions because it can help you see. If you just did it one time and did it in the year that was bad yield, you might say, well, genotypes all have the same. Well, no, they're not. It's just that in that particular environment they weren't able to express their differences in that environment because maybe it just didn't rain much or something, so they all did bad. It's also a good idea to always look at the data before you go ahead and fit stat models because it can help give you a hint on what is an appropriate model to fit to the data. So what we're going to do for the rest of this lesson is basically slowly build up. That's a pretty complicated model that we want to fit, right? It's got to have treatment and genotype, their interaction. It's got to have something to account for the non-independence of the split plot design, and it's got to have environment replicated. So it's like, well, that's kind of complicated. Let's simplify things a little bit and just start and just subset the data to just have one of the environments, one out of these 6. We're just going to take that data and fit a model to it just. And not to mention, we're actually going to make it even simpler and just fit the model for the random effect. We're not even going to look at treatment and genotype yet, because I want to show you how the random effects work, how we're going to account for the experimental design. The fact that if you go back to the reason we have to care about this is like in this setup, right? Measurements from the same block are considered to be correlated with each other because they come from the same place. So like if the soil was better in this block, all the measurements from that block are going to be better on yield, right? And you would think that like because they're closer together, they would tend to have more similar results. And same with the main plots are all physically next to each other, so we have to account for that as well. So that's what the random effects are going to do for us. They're going to help us average out those environmental unknown influences we can't measure in order to be able to have a better estimate of what the treatment and genotype effects that we care about. We're just sort of like trying to account for those. Again, this is how you do it in SAS, but I won't dwell on that. It's just there for your reference. Okay, this is the model formula. Basically, the main part of this slide is the model formula. I have a lot of explanation of it, but this is a model for just one environment, not caring about the treatments, just caring about the random effects. Just like we have had before, the response variable is yield. It's on the left-hand side. That's what we're trying to predict. That's our y variable. Then you have the tilde to separate the left and right-hand side. And then this side is where all the model predictors go, the fixed and random effects. But like I said, we're not going to do any treatment effects yet. So we're just going to fit an overall intercept. What is the overall average yield in the whole data set? We're just going to put a 1 there for the fixed effect. And then the random effects, we have 2 levels of random effect. A random intercept for each block. So we're saying the measurements in each block are correlated. And a random intercept for each of those halves, the main plot. So that's, we say sowing : block, which means each combination of sowing and block gets its own intercept. So if you go back to let me just go back there. Right, so this whole thing's a block. It gets its own intercept. 1, 2, 3, 4. There's gonna be 4 of them. And each of these main plots gets its own intercept as well. We have 8 of them. So it's sowing by block because screening is a sowing treatment. So this is block 1 sowing treatment. It's a 1/2 plot. It gets its own intercept too. Everyone got that? So where were we? Yes, so that's the model formula part. Let's put it into our function. We're going to say, I'm calling it fit one environment. We're going to use the LMER function because we're fitting a mixed model. There's the formula we just discussed, is the first argument. There's the data that we're going to plot, or that we're going to get the data from to fit the model. And since I told you we're only going to do one environment, I use the subset argument, which will subset the data to we're only going to consider one location and 1 year. Location and equals means everything where location is equal to Appiano and everything where year is equal to 2002 to 2003. We use the ampersand sign to say and. So both of those things have to be true to keep that subset. So I've left a decent amount of blanks for you to fill in. This is the LMER function. Our response variable is yield, has to be capitalized. Right, we have an overall intercept. Then we have a random intercept at the level of block. And we have a random intercept at the level of sowing : block, which means each combination of sowing and block. And data equals fava means that's where the data come from that we're going to use for the model. On that, And we can use the summary function on this fit_1 environment. Again, you can start typing it and then hit tab and it'll complete it for you. And you hit control enter. Okay, what does it tell us? We've got an intercept. The average yield across the whole data set, basically accounting for the random effect, is 1.7. I don't know what that is, tons per hectare or something. And then it tells us where the variance is in the data. Is it at the level of plot, main plot? Is it at the level of block, or is it at the level of the individual subplots, the residuals? It tells you what the variance is for each one. And it looks like the variance for block is very, very tiny, so it's almost zero. So we can see that once we've accounted for the main plot and the subplot, there's not much variance left to explain by block if we're just looking at the random effects. We can use the ranF function to actually look at what the individual random effects for the different blocks are and the different plots. So it's like this basically this shows for each of these main plots what is their yield difference from the overall average. And if you look at it, like autumn 1 has like a little bit higher yield than you'd expect by average, and spring 1 has a little bit lower. And if you look at it, all the autumn ones have higher and all the spring ones have lower, and that's because we didn't put the treatment into the model yet. Once we put treatment into the model, we wouldn't want to see that in real life. I'm just slowly building you up to the right model. We haven't even put treatment in the model yet. So it makes sense. We're like, look, all variation between the plots is random. It's telling us that these ones have higher and these ones have lower. Once we put treatment in, that will explain some of that variation, and we won't have those same residuals anymore. And another thing we can do is use ICC. That's called intra-class correlation coefficient. That's a way you can look at the percent of variation explained by each type of random effect. So we could use ICC, and you can say by group equals true, which will give you the ICC for each level of random effect. And since we have the two random effects are the main plot, the sowing by block, and the block, it's very high for the sowing by block and almost zero for the block, which we saw already in the model summary. Any questions? So yeah, that's how you do it. Now, the next thing we're going to do is actually look at the treatment effects. That was just to set up the model to make sure that the model structure is capturing the experimental design, which we're good with. Now we want to actually put our treatments into the model, since that's like the whole thing we care about. We're still working on just one environment. I haven't taken this to the full data set yet. We're still just working with the one environment. So here's the fixed effects. The way you would do them is separate them by plus signs. We want to look at the treatment effect, or I'm sorry, the genotype effect, plus the treatment effect. Sowing is the name of that treatment column, plus genotype : sowing, which means the interaction of genotype and sowing. So we have the two main effects and interaction effect. Is the effect of genotype different between each sowing treatment? And you can also use a shorthand. Genotype * sowing means give me, if I have two variables, give me both main effects plus an interaction. So that is the same as that. This is just like a shortcut. Genotype * sowing is the same as saying genotype plus sowing plus interaction of genotype and sowing. It means all combinations. So basically, this is a new one, fit one environment fixed effect. It's exactly the same as the last time, except here before where it says genotype by sowing, we used to only have a 1. Now we're putting genotype by sowing there. That's going to put in those treatment effects in the model. So that's what we're going to do. Yes, that's the only change between the previous one is right here. genotype times or asterisk sewing. Same subset and everything as before. Now we can look at the summary to look at those effects. I'm going to hit Control Enter on this summary line here. And you can see there's a lot more going on because now we have a lot of fixed effects that have correlation between them. But we can basically, you can see there's a lot of coefficients in the model now that we're estimating, not just an intercept, but we also have basically a parameter for each genotype showing how different they are from, well, so there's 5 genotypes, there's 6 genotypes, we get 5 parameters because the first genotype is the intercept. So if the first genotype by default in alphabetical order is the intercept, it has a mean of 2.4, and then this Colomeno is minus 0.17 less than that. And we also have this sewing spring is the average effect of the sewing treatment in spring relative to autumn. So spring has a lower yield than autumn. That's why it's negative. And we saw that when we looked at the graph. And these are the interactions for each genotype. And we also see now our random effect variance is less anymore because we've used the treatment to explain some of the variations. So now the block level variation that is not explained by treatment and the plot level variation is less, which we would expect because we want treatment to explain some of the variation in the data. So it's good if this is a low number. And you can look at the random effects. If you hit Control Enter, Ran F, you can see there's now they're a little bit more random. Like some of the autumn ones are negative and some are positive. Some of the springs are negative and some of the springs are positive. So like those individual plots maybe were a little bit lower or higher. We don't really know why, because this is beyond what treatment is explaining. Same thing as, and then we can also look at the ICC to see that as well. We now see right before, remember how the sewing by block had 0.78. If you go back up, you can see it was 0.78. Now they're a lot lower, which is overall, which is good, which means we have less random variation because we've explained more of the variation with the thing we actually care about, which is genotype and treatment. Any questions? All righty, so y'all have been very patient today. It's great that you're still paying attention at 3 o'clock. We'll wrap this up in a few minutes here, and then we'll have time for questions or any thing we want to discuss. Yes. So the other point I have on the slide here is that it gives you all this output about correlation between the fixed effects, which I kind of glossed over. You can ignore this because in an experimental data, we have experimentally randomized which plots get which treatment. If you had an observational data, you might have correlation between the predictor variables, right? Like if you wanted to look at like whether income and tobacco use predict cancer and just measured a bunch of people, those two things might be correlated. And so you'd want to like account for the correlation between them if you want to look at their effect on disease. But here we don't have to care about those correlations because we have actually randomized which plots get which genotype and which treatment. Don't have to worry about that. If you were doing an observational study, you may not like those to be high numbers, but it doesn't matter here because we know it's random. Yes, and you can get an ANOVA table for this model as well. I usually recommend that people do not care about that because unless you're like trying to look at heritability and look at the variance components, G by E interaction and that kind of thing, really, if what you really want to do is compare the means between the genotypes and the treatments, you should just do the post hoc test and compare the means directly and not care what the ANOVA says. So I'll just say that here for reference, and we're gonna actually do some of that means comparison in just a minute. But I would not worry about the ANOVA table here. Okay, so now we've fit a model to just one of those 6 environments. The last model, I think, I'm pretty sure, that we're going to fit today is a model. Well, we're going to do a few different versions of this, but we're now going to fit a model to the full data set with all 6 environments. Now, some people ask me, well, is environment supposed to be a fixed effect or a random effect if you have a mixed model? Well, I have to say it depends, because basically what a fixed effect would be good for is if you specifically want to compare the means of those different environments, then you would consider it a fixed effect. But if you consider the environments a sample from a population of potential environments you could have done the study at, then, and don't really want to compare the means of those specific environments, that's when you want to be a random effect. Like let's say you were doing a medical study testing the effect of a drug given to patients in different hospitals. You have to pick some hospitals to do the study at. Like let's say you did the study at 10 different hospitals. You don't necessarily care about comparing hospital A versus hospital B. You just want to know, these are like, you sort of selected those hospitals randomly from any possible hospitals you could have chosen that are in the world. So that would be like a random effect. Like if you did a study in this field right out here and did different blocks in that field, somebody else wants to replicate your study in another state or whatever, they can't use your same field. Those are like one of a kind blocks that you chose these locations kind of from a population of locations in the world. So it makes sense to have them as a random effect. Yeah, like if you did the study again also, you'd have to do it in a different environment, because even if you did it in the same place, it'd be at a different time, which is kind of a different environment. So they're one of a kind. That's why we call them random effects. And now that we're going to do this on all the data set, not just the one environment, we now have to have and we're going to treat environment as random here. We're going to do even more random intercept terms, right? We have to have a random term for the environment, the location by year combination we had. And now we have to actually have a separate term for each block within each environment and each main plot within each block within each environment. That's kind of a mouthful. Yeah, if you go back to the figure, where were we? Yeah, so, right, each row of these is an environment to get a random intercept, and then this block is just one within an environment. It gets an intercept, and then each plot within each block. So there's 3 levels of variation here that we're caring about: the environment, the block, the main plot, and then the individual data points are those little squares, the subplots. Going back to where we were. Right, so let's fit this model. It's got, we call it fit all environments. It has the same fixed effects. Now it has environment is one of the random intercepts, combination of block and environment, and sewing treatment block environment combination. Each of those gets its own random intercept. And we're not going to use subset anymore, because we're just going to use the full data set, fit to all environments. Let's do that. So first, environment is a random intercept term, block by environment, and sewing by block by environment. All 3 of those have to be in there. Okay, and now we're going to run that. Okay, so we get some angry red text. If you have a different color scheme, it's not red, but this is it's not an error message necessarily. It's just a message. Like the model still runs, but we get a message that says there's a singular fit, a boundary singular fit. What does that mean? You can't really just ignore that necessarily. You need to at least figure out what it is and what might be going on with your data. So what it means in statistical jargon language, it means at least one of the terms in the variance covariance matrix of the random effect or a linear combination of that is exactly 0 or exactly 1. So what is that? That's like not very understandable. So what does that actually mean? It means the algorithm that is being used to fit this model to get the parameters does not have enough data to get a good estimate for all those parameters. Usually what that means is we're trying to fit a too complicated of a model to a too small of a data set to get enough information to fit that model. Some of the random effects are very small and they can't be told apart from 0. The algorithm just kind of fails and says, well, it's 0. It's too small to tell. Or some of the random effects are perfectly correlated with each other. And when you know one, the other one is giving no extra information. So basically, the model is too complicated for the data set. What do we do in that case? Well, we can take a look at the variance covariance matrix to actually see which terms are 0 and see which ones are not explaining any variation. And usually this is the random effect that causes this issue. So we're going to use the var core function to take a look at that. Let's take a look. And we call this fit underscore all environments. You can put tab to finish typing that. Let's take a look at what does it show. Okay, you see how this one is 0 exactly, right? The environments have a pretty high standard deviation. There's a lot of variation between environments. The main plots have some, but the blocks have exactly 0. So, well, that's not good. What can we do? Well, we can simplify the model by getting rid of the random effect terms that don't explain any variation and refit the model. Or some people say, well, just go ahead with it. If those terms are 0, they're not going to make any difference anyway. But it sort of depends on your philosophy on that. But we're going to just go ahead and refit the model. Since block had no variance, we're going to just get rid of it. And I'm going to call this fit all environments with no block term. We're just going to use the environment and the plot within block within environment as a random effect. We're going to get rid of the block term. Just have those two. And so, yes, so we're just gonna have one pipe sewing :block : environment. Right. Other than that, it's all the same. It's the same as up here, except we don't have this part anymore. We got rid of it. Other than that, it's all the same. So it has a more reduced random effect specification on it. We'll run that. We do not get the singular fit message anymore. So we've simplified the model enough that we can get a good estimate of all the parameters. We're going to use the check model function again to get some of the diagnostic plots. I've added some extra code to only produce the ones that we care about. In the previous lesson, I didn't do that, and it spit out a bunch of plots that I didn't even mention. But here, we're just going to look at the ones we care about. We're going to use check model for that. Check underscore model is the function, and check is the name of the argument that means show me only these plots. If you zoom in, you see it all looks good because there is no trend in the residual. There's not really much trend in the variance. It's pretty flat, and there's not hardly any of the points are off the line, indicating they're pretty close to normally distributed. So we can say, well, this model meets the assumptions. We can use it to make predictions. It's going to give us a valid answer. So we're good there. But before we go to that point, I did also want to give you the option of having random slopes as well. Now, so far, we only fit a random intercept model. That means the environments can have different means, but the effect of treatment is going to be the same in every environment. You could also do this by block and even finer than environment. We're just going to look at environment right now. So we do this. If you look, let me show you the data again. Yes, if you look, it would kind of make sense to allow the treatment effects to be different between environments, right? Because in some environments, autumn has a higher mean. In other environments, I would say there's really no difference between spring and autumn here, right? The pink and blue have about the same. There's no difference. In a lot of environments, there is a difference. In some, there's not. So a model that is not going to take that into consideration might not give you good predictions because it's not going to account for the fact that different environments may have different, the treatment may work better in some environments than others, right? So we're going to account for that now with a random slope. That means not only can the average, right, like the average of this environment is way lower. So we're accounting for that. It's higher here and lower here. We're accounting for that. But we haven't yet accounted for the treatments to actually be different in how much their effect is in the different environments. That's what we're going to do when we throw in some random slopes. How do we do it? Well, we add additional terms to the random effect formula. Instead of just having a 1, we're going to add some more random terms. Genotype and sowing, that means we now have more additional a random slope for genotype. So the genotype effect may vary by environment, and the sowing treatment effect may also vary by environment. So we say fit all environment with all random slopes. You can see this is the same as the one we had previously, where we have yield is a function of genotype and sowing are the fixed effects. We have random effects for environment, and we have random effect for the plot within environment. But now, instead of just having a 1 here, we have 1 plus genotype plus sowing. So the only change we've made to the previous model is this part is now added in. Those are our random slopes. So let's go ahead and add those. 1 plus, so a random intercept, a random slope for genotype, and a random slope for sowing by each environment. And you can see the other one, the plot, we're just going to keep having the same, just a random intercept. Okay, so once again, we get a singular fit. What does that mean? It means the model is once again too complex for the data we have. We're trying to do too many different parameters by throwing in all these random slopes. So if you look at the variance covariance matrix of it, let's take a look at that. Hit Control Enter. It's like, wow, that's a lot. I mean, there's just a huge matrix of numbers there. None of them seem to be 0 or 1. So we're kind of like, we are at a loss for, we can't just easily say which of these terms should we get rid of. But what should we do here? Well, it looks like adding a random effect for genotype is adding just a lot of parameters because there's 6 genotypes, so it adds 5 different random slope parameters. So I think we should probably try to get rid of that genotype random slope because it's making the model way more complex than it needs to be. And we already saw that clearly the sowing treatment has a very different effect in the different environments. So we definitely want to include that random slope. So let's see if getting rid of just the genotype random slope and keeping the sowing one will simplify things just enough that we can get a good answer. So how are we going to do that? Yes, just like the previous one, except instead of having here 1 plus genotype plus sowing, we just have 1 plus sowing. That's the only difference between this one and the one last time. We've just got rid of the 1 plus genotype plus sowing, just says 1 plus sowing. That's it. So we're going to do that. Yes, 1 plus sowing in each environment. And we're going to hit Control Enter to run that. And you can see it does not say singular fit anymore. So we've simplified the model enough that it's giving us a good answer. And you can look at the random effect by environment if you use this code here. So let's look at that. And F is the random effect, and this $ environment means pull out just the random slope and intercepts for environment. You can see that the random effect, the random slope for sowing in these 2003 through 2004 is positive, meaning the effect of the spring sowing is more positive or less negative in those environments, which is kind of what we see by looking at here. Yeah, like here the effect of spring is very negative. Here it's less negative. It's basically 0. So that's being captured in the statistical model. So that's good. We want that. And we can use check model. This is just a good practice to look at the diagnostic plots and just make sure once again that they look good. Once again, it all looks good. All those lines are flat and straight, which is what we want. No trend in the residuals. That's good. And I just want to show you how we would compare all. We fit a bunch of different models. We kind of argued that the random slope one with sowing random slope is the best. We can actually show that it's a better fit to the data than the other models we've tried by using AIC, which is an information criterion. What that does is basically it tells you which model is the best fit to the data, accounting for if a model is too complicated, it will get penalized. So it'll tell you which model strikes the best balance between being a good fit to the data and not being too complicated. If it strikes that best sweet spot, it's going to have the best AIC score. And the lower the AIC, the better. So lower the AIC means a better fit. So we're going to compare all the models we did so far to the one fit to all environments, the one without a block random term, the one with all the random slopes, and the final one we did with just the random slope for sowing. We did 4 models there. So let's compare them all and see how they do. AIC is what we're going to use. And you can see that the lowest AIC is for that final one we just did, which does include the random slope for the sowing term. The ones without any random slope do much worse. The 2 random slope models do the best, and the slightly simpler one we found is better. So that kind of confirms our intuition that we have. Any questions on that? Okay, we're in the home stretch here. So yeah, this is I don't know if you all have seen this meme before, but we also want to keep in mind that statistical models are all relative. AIC can only compare models to each other. It's all relative. You can't say if one is good or bad. It only says if one is better relatively than another. Like maybe all these models are terrible. We didn't really capture the truth. We don't know. All we can say is like at least it's better than these alternatives. But if you're like an applied scientist, they don't understand the limitations of statistics as much as we statisticians do. So get freaked out when their stat models don't work. But statisticians know that stat models are just imperfect tools, and so we're like very enlightened about it, you know. Yeah. So it's all relative. The last thing in terms of content that I want to go through today before just doing the final wrap up and how to present these results is I told you we want to actually compare the means. Like we made a bunch of graphs and plots, and that was cool. And we also have all these numbers here, but we don't actually have an estimate of the means of each genotype and treatment from the model or p-values comparing them, which is kind of what you want. So why don't we just do that, which that's kind of like the bottom line result that you want to present. So we're going to just knock that one out while you all are still paying attention. So we're going to use what's called estimated marginal means. So some people know them as least square means or LS means because that's what SAS calls them. And SAS, well, the statisticians at SAS didn't exactly invent it, but they popularized the concept. And basically what it is the expected value or the model's estimated value of the mean of each treatment averaging over any other effects in the model. So like if we wanted to compare the genotype means, we could average over the treatments, we could average over any random effects, everything's averaged out, we just get the means for each genotype. And there's like ways to get degrees of freedom so that you can calculate a confidence interval on those means and then compare each pair of means basically with a test statistic and get a p-value to say, are they significantly different? And there, we're going to use the R package called EM means, estimated marginal means, that this guy, Russ, he's a retired statistician, but he still works kind of like as a hobby, maintaining this R package. And every time people like me like ask him to add new stuff to the package, he does. And I'm not sure where he finds the time or why he does it, but I appreciate it. And it does everything SAS does with the LS means and then some. So it's a great resource. That's how you do it in SAS. I'll skip that. Basically, the way we're going to do it in R is using the EM means function. And the syntax of it is we say EM means is the function. The fit is what model are we going to use to calculate those EM means. And every time, since we decided this final model with the sowing random slope was the best model, out of all the alternatives we chose, that's the one we're going to use to make predictions. And then you say by or tilde whatever fixed effects you want to get the estimated marginal mean for. So we're going to do it 4 different ways. First, we're going to get the estimates for each genotype averaged over everything else. We're going to get the means for each sowing treatment average over everything else. And we're going to do the if you say genotype plus sowing, that'll compare all 12 combinations to each other, which gives you a lot of comparisons. Because if you compare 12 means to each other, you're comparing 11 plus 10 plus 9. You're comparing a lot of comparisons. But if you do genotype pipe sowing, that means within each of the 2 sowing treatments, compare the 6 genotypes to each other. So that's a little more manageable and be really more what you're interested in. Those are the 4 ways we're going to do it. So let's run each of those 4 real quick, and then we'll look at what they show. EM means is the function every time. The first one, we're going to look at the means by genotype. We're going to do by sowing. We're going to do by genotype plus sowing. And we're going to do by genotype vertical pipe within each level of sowing. So then we'll highlight that block of code and run all of it. And it gives you a note, the results may be misleading due to involvement in interactions, which means if you have an interaction effect and you're comparing the means of genotypes, averaging over that interaction, it may give you a misleading result because you're ignoring any possible interaction with treatment. But let's look at so the means for each genotype. If we look at EMM_geno and just type that in and hit enter, it'll show you the means. You can see here are the means for each genotype and their confidence intervals. Averaging over all the environments and averaging over all the treatments, it's saying that like the Palomeno has a very low mean 2.8 and Scuro looks like the highest. And there's the confidence intervals, although they're very overlapping. If you look at the means for each sowing treatment, you can see that Autumn had a higher mean overall, averaging over everything, which we saw from the data. And if you do by the way, if you double click on a variable name, just it, and hit Control Enter, it will just print that in the console. So I'm just going to do that. So this is genotype by sowing. You can see here are the means for all the genotypes in the Autumn. and here are the means for all the genotypes in the spring. And let's, without having to go look at every number, a better way to, we can make a plot of this so that you can actually visualize it better. I'll do that in just a second. But before I make the plot, let's actually get p-values of treatment contrasts comparing these means to each other. That's what y'all are here for, right? P-values. So we're gonna do first the contrast function means compare each pair of means in the estimated marginal means. And if you are familiar with post hoc tests, you usually have to do an adjustment to the p-value because we are making more than one hypothesis test, right? If we have 6 genotypes, there's 15 ways to compare 2 out of 6. You can, there's you can compare 1 with 2, 1 with 3. There's 15 ways to compare them. So we're making 15 hypotheses. We have to adjust our p-value so we're not overestimating the probability of getting a false positive, or we're reducing our probability of getting a false positive by adjusting the p-value. And there's different adjustments you can use, like Tukey test and that kind of thing. CDAC adjustment is kind of like the more conservative one, so that's what we're going to use here. We don't have to do that for the sowing one because we're just comparing autumn versus spring. We're only testing one hypothesis because there's only 2 means. We don't have to do an adjustment because there's only one p-value. No need to adjust for multiple p-values. And we say pairwise because there's other different types of contrast you can do. We're going to do pairwise, which means compare every pair of means. So we'll do contrast of the genotype means. We're going to say it's going to be pairwise contrast. And the adjustment method is CDAC. Control Enter. Now we get a p-value for every, so this is saying, well, Chiaro has a higher mean than Colomeno by this amount, and that's significantly different. P-value is close to 0. Some are not different. Chiaro and Palumbo or whatever their difference is only 0.1, and that is not significantly different after adjusting for multiple comparisons. If we did the contrast of the sowing treatment, you can see that autumn minus spring, the estimate of that is 0.88. So that means autumn mean minus spring mean is positive. So autumn has a higher average estimated than spring, significant. And the contrast of genotype and sowing combinations, I'll just show you real quick. It's way too many comparisons to look at. If you look at it, it'll take a second because it's comparing all 12 combinations of genotype and treatment to each other. Sometimes this server runs slowly, so this should go quicker if you're doing it on your own machine. So yeah, we're comparing like all the possible combinations, like, Chiaro in autumn to Vesuvio in spring or whatever. I usually don't do this because this is probably not what you're looking for. This is more comparisons than we really want. What we want is to compare, what often you want is to compare the genotypes within each level of treatment. So we can do that comparing this other one where we did genotype pipe sowing instead of genotype plus sowing. So now you can see we've compared each pair of genotypes in autumn treatment, and we've compared each pair in spring treatment. And if you look at it, I won't go through all the results, but you can see there's some interaction where in the spring, some genotypes are different. Like this genotype is different from the other in spring significantly. But if you look at the same one in autumn, it's not significantly different. So there's an interaction between genotype and treatment. So if you just looked at genotype, it might give you, it would say, well, if you just look at genotype, it's telling you these 2 genotypes are significantly different, but it's ignoring the interaction. Really, that depends on the treatment. They are different in one season, but not the other significantly. So that that's why you have to consider those interactions. So I just showed that. And people oftentimes want to present in a manuscript the letters to summarize the multiple comparisons, where you have A, B, and B, and that kind of thing, to show if two means have different letters, they are shown to be significantly different. So all that's doing is like putting those p-values and converting them into a shorthand summary. I still like to present the actual p-values, but if you have a lot of means, it can be to compare them more concisely with this. So CLD, which stands for compact letter display, is the name of the function in R that is used to convert those EM means to a set of letters summarizing the multiple comparisons. So we'll do that real quick. And yes, CLD, and this letters equals letters part, which seems weird, it's by default, I don't know why this function gives the groups as 1, 2, and 3, but most journals use A, B, and C. So you have to put this letters equals letters to get that. So if we're doing just genotype, we get, we'll use CLD for that. You can see that this is just kind of a summary of those significant differences. Some are significant and some are not. So it said that Colomeno is significantly lower than, is not significantly different from Vesuvio because they share a letter, but is significantly different from all the other ones. But again, that's ignoring the interactions. If you do the CLD of the one of genotypes within each sewing treatment and run that with the same multiple comparison adjustment CDAC that we used before, you can see that there's kind of a bit of an interaction between genotype and treatment, because well, this one is lowest in both, but Palumbo, for example, is the best yielding in autumn, but it's actually not very good in spring. So that's there's clearly an interaction there, which if you just averaged over treatment would not see that. It would give you a misleading result. So that's why it's important to do that. Okay, is that it? Yes, that's it. So I didn't show in this one how to make a plot of that, but I can, if people really want that, I can add that code later on. But now that's a table similar to what you might present in a manuscript. So that's kind of the final product here, is the table of multiple comparisons. You could also show that graphically if you plotted these lower and upper confidence limit as error bars on each mean. You could show it as a plot. Yes, so it's now a bit after 3:30, so I'll just finish by going over. Now you should be proud of yourselves, because look at all the stuff that you just learned. You know how to fit linear mixed model to a split plot data that's repeated at multiple locations with random intercepts and random slopes. If the computer tells you it's a singular fit, you can fix that, and you can even estimate means from the model and compare them with a post hoc test. Like that's pretty good. So you should let's give ourselves a round of applause. Come on, let's do it. All right. Yeah, very nice. And yes, that is everything that I have. So I think I'll stay here and answer anyone's questions. Yeah.